All right, hello class. We are moving away from related rates and implicit differentiation for a little bit to talk about some more applications of the derivative. So we're right into the next module, which is applications of the derivative. And this one you may have gotten a sense of already, and that's to do with critical points and what they tell us about a function. So we already have this idea that when the derivative is 0, that corresponds to when the function likely turns around, right? When a function turns around, like this one here, goes from increasing to decreasing, at some point here, we get a horizontal tangent line. In other words, the derivative is 0. Okay, or we might have a situation like this where we have a spike or a cusp, and this is where f prime is undefined. But this is also a place where we have, say, a turning point, and one we may not have discussed yet, or you may not have come across yet. I maybe didn't draw it super well, but you could also have a horizontal tangent line. Even though the function isn't turning around, it just sort of levels off for a moment. That would still be where the derivative is equal to 0. Well, all of these situations here are what's called critical points. Okay? Critical points are essentially where you might have a turning point, where the derivative is 0 or undefined. Okay, so specifically C is a critical point of f of x if f prime of c equals 0 or f prime of c is undefined. And why they're called critical points is really because something interesting is happening at a critical point. Right? So what do I mean something interesting is happening? Well, just like what we said before, if the derivative is 0, that's likely where we have a turning point, right? Which would abbreviate as TP, turning point. So this is where f prime is 0, or it's a leveling point. Okay, and also where the derivative doesn't exist is also something interesting happening, possibly a spike. Now, I do need to be a little rigorous here, so I do avoid some of the rigor sometimes while teaching, but C in this case, okay, it has to be an interior point of the domain of f. So that means if C is not in the domain of f, it can't be a critical point, right? So if you have a blow-up point for the original function, that same point is not going to be a critical point. It's just another point where the derivative also doesn't exist. Also, that means interior means if the domain of f is something like 0 to 10, 0 and 10 aren't considered critical points of the function, even if they would make the derivative equal to 0, because, well, you can't check both sides of it, right, to calculate the limit. So really, the critical point needs to be somewhere in the interior of the domain. Now that is very, very specific here, but there are a couple of problems we might run into where we need to be very careful about that. All right, so that's just a bit of housekeeping there. Importantly though, this turning point, this is what we would call, depending, well, it looks like what we would call a local maximum. Now, I'm certain from your pre-calc class you've probably talked about maxes and mins of a function, okay, and that's essentially what critical points can lead us to. Right, so critical points can point us to the possible local and absolute extremes of a function. And I don't want to give you the word definitions for these absolute extremes. I think just with a graph it's probably a lot nicer to look at and talk about, but something like this, let's say, And let's say we have a closed interval that this function lives on. Okay, so here is what we would call a local max, right? Because it is the highest value locally, right? It's not the highest value ever because there are some higher values up here, but around here it is the highest value, and it's basically a turning point where we go from increasing to decreasing. Okay, this is also a local max. This is a local max. Okay, this right here, this is a local max and what we would call the absolute max. And it's an absolute max because it's the actual highest point of the graph on this domain. Okay, then similarly, if we go through, this right here would be a local min, right? Because it's the lowest point locally, and it's a turning point where we go from decreasing to increasing. Okay, so this is a local min, this is a local min, this is a local min, but it's not an absolute minimum because this point is actually lower, right? So this endpoint here, okay, is the absolute min of the graph because it is the actual lowest point of the graph. All right, now I do want to mention you don't always have local maxes and mins or absolute maxes and mins. Okay, there are plenty of times where you won't actually end up with those. And notice this endpoint it's nothing, it's just an endpoint. Because this ends up being lower by just a little bit. Okay, but this idea that what hopefully you'll notice is at every local max and every local min, at least with the way I've drawn this with a smooth function, right? Every local max and local min is at a critical point, and the absolute maxes and mins live at either a critical point or an end point. Okay, so just to write that down, all local extrema live at a critical point. I usually abbreviate critical point as CP. And all absolute extrema live at either an endpoint or a critical point. Extrema is just a word that encapsulates maxima and minima, which are the, believe it or not, the plural of maximum and minimum. But it's just a catch-all for either. Okay, but this was a smooth graph. This idea can also work if it's not a smooth graph. Okay, now when looking at graphs, we have to be kind of, well, we have to be a little bit, I guess, predictive and just assuming that the graph continues to behave in the way that we see, unless we're specifically told that it has a closed domain like we did in the last one. But here, this graph seems to just go on forever and ever and seems to continue decreasing down this way and down this way. So if we were to take the limit of this function as x goes to either positive or negative infinity would be negative infinity on either side. However, this right here is a local max and an absolute max, and specifically the absolute max because, well, not only is it the highest point locally, it's the highest point of all time. Right? It's the highest actual point. Okay, right around in here somewhere, we also have another local max. Right, but these are two separate types. Here it's a spike, so this is where f prime is undefined. here is where f prime is equal to 0. Okay. Similarly here, this is a local min, right, because it's the lowest point around, and this is also a place where f prime will be undefined. However, one thing to note, there is no absolute minimum because the graph continues to go down on both sides forever, right? So there's absolutely no absolute minimum. All right. If this were our graph here in blue, this point right here would be a local max. Right? This one would be a local min. Okay, however, there would be no absolute extrema because, well, the function goes down to negative infinity on the negative side and up to positive infinity on the positive x side, so there's no absolute extrema. All right, now this concept might get a little more complicated than you might expect. Say for this function, it may be fairly clear that this point right here is the absolute minimum, right? Because there's no point lower than it on the graph. However, this open dot right here is not an absolute max because there's no point here. We can't plug in a point and say it's the highest in the graph because this is one of those cases where we could continue to zoom in closer and closer and closer and keep finding values higher and higher and higher and do it over and over and over again. So when you have a hole as your highest point, we basically have no absolute max here. There's also no local extremes. We can't say that this is a local max because if we take x's around it, well, there's definitely points higher than it. Okay, so this basically just has an absolute minimum, and that's pretty much it. Okay, some other possibilities. Here we have a place where the function just levels off, so this is neither a local max nor local min, but instead a point where the function levels off. It's still a place where f prime is equal to 0. Okay, another possibility is if we essentially just flip this around. All right, so say our graph does this. All right, so pretend it doesn't actually get vertical, right? It's still a function, but it has a point with a vertical tangent line. Right, this is a place where f prime would be undefined. All right, the function itself is continuous. It's still a function. It's still fine. It just has a little blow-up point. You could see something like that in the cubed root of x. And this, for example, you could see in x cubed. Okay? So instead of a leveling off point, you could think of it as a verticaling off point, where it sort of becomes vertical for just 1 millisecond and then jumps off to being, well, still being, in this case, decreasing again. So basically decreasing to decreasing, but it's basically, we'll talk about what these points are in a later section, but these are what we will eventually be calling inflection points because it's where behavior of the function changes, but not necessarily whether it's turning around. Something else is going on. Okay, you can think of it as where the acceleration changes. Okay, all right. Okay, before we start looking at some examples of finding these analytically, keep in mind that absolute maxes and mins can occur multiple times. Take the graph of sine. Its absolute max is always 1, but it happens an infinite number of times, right, at an infinite number of values. This only happens if you have the same y value over and over and over again, but it is still the highest y value. So for sine, the highest y value is 1, and it occurs a huge number of times. Same with the absolute minimum. We have the absolute minimum of sine is -1, and it occurs an infinite number of times. Okay, so just wanted to clarify that before we really move on. It is possible to have an absolute max or min show up multiple times, but only if the y values are the same. All right, so the first technique we're really going to focus on, and mainly this is what we will be looking at currently in this lesson, is just finding absolute extrema. In a later section, we're going to look at finding local extrema, but for right now, I want to focus more on finding critical points, and then once you find them, it's pretty easy to find absolute extrema, provided you're on a closed interval, because essentially, if f of x is continuous on a closed and bounded interval, say a to b closed, then f attains an absolute max and min, and they must occur at either the endpoints or the critical points. So that's kind of like what we were talking about earlier, that if you make a function continuous on a closed and bounded interval, well, you can't do that without making sure that the function has, say, an absolute max and an absolute min, and they can occur either at the endpoints or on the interior at critical points. And if the function's not smooth, it doesn't have to be smooth, it can still be just continuous. Once again, its absolute max would occur here and min here. Okay? Now, if it's not a closed interval, say if it's open, you could have situations like this, where you would have no absolute max or min. If the interval's not bounded, you can have situations like this, where the function goes on forever in every direction, and there's no absolute max or min either. But if you are on a closed, bounded interval and the function is continuous, you must have an absolute max and an absolute min, and they will only ever occur at critical points and or at the endpoints. Okay, so that means finding absolute extrema comes down to essentially just finding the critical points and then plugging everything in, critical points and endpoints, into the function and seeing what values are the highest and the lowest. All right, so essentially to find absolute extrema on a closed interval, a to b, it essentially boils down to this. You find the critical points. So in order to do that, you set f prime equal to 0 and solve. And you check where f prime is undefined. Then you plug the critical points and a and b into f and see which is the highest and which is the lowest. Okay, the very highest will be your absolute max. Your complete lowest will be your absolute min. All right, so let's start with a fairly simple example, and we will increase the complexity as usual. All right, so let's find the absolute extrema of f of x equals x cubed minus 3x squared on the interval -1 to 3 closed. Okay, so we're going to find the critical points, so that's where we'll start. And to do that, we first need to find f prime. So f prime of x is going to be, well, it's just power rules here, so 3x squared minus 6x. Okay, and then we set this equal to 0. How I usually do this, to save having to draw another line, this is just my notation, but I often put a three-pronged equal sign just to say that I'm setting it equal to 0. That's just my notation, but it's probably unnecessary. Anyway, we are now setting this equation 3x squared minus 6x equal to 0, so they both share 3x, so I'll factor that out. We'll get a 3x times x minus 2 equals 0. So x is equal to 0 or x is equal to 2. And there we go. Those are the critical points. Now both of those are in this interval, -1 to 3. So now we're just going to check the critical points and the endpoints. CPs and endpoints. Okay, so I just go down the line. F of -1, f of 0, f of 2, and f of 3. Okay, now f, it's kind of off the screen now. If we go back and remember, it was, let me write it over here, x cubed minus 3x squared. So here is a really good example of why we need to be careful about how we label things, even if it's just in your own work, because this is f prime, right, that we solved for. Now we're plugging into f. So we don't want to be plugging into f prime, we want to be plugging into f. So that's something you should be very, very careful about. Now I won't go through all the details of plugging these in. I hope by now you can just plug values into a function. But cranking these out, we'll get the following values. All right, so f of -1 is -4, f of 0 is 0, f of 2 is -4, and f of 3 is 0. So it turns out that here is our absolute mins, and here at 0, let's change the color there, here at 0 is our absolute maxes. So our absolute min is -4, but it occurs at both -1 and 2, and our absolute maximums are at 0, and they occur at x equals 0 and x equals 3. So if we go quickly to the graph to see how this lines up, hopefully it will. Okay, and here I've graphed the function and restricted it to that domain that we were given, -1 to 3. And as we can see, we have absolute maxes, one at a critical point, one at an endpoint. We have absolute minimums, one at an endpoint and one at a critical point. All right, so specifically you could say that the absolute minimums are the points -1, -4, and 2, -4. And the absolute maxes are the points 0, 0, and 3, 0. Okay, technically they are points. Okay, you'll find that I'm a little non-rigorous about, what is a point and what is a value and all that kind of stuff. Mainly because there's a lot of stuff flying around, a lot of stuff to be talking about, a lot of words to be used. But technically these are points on the graph. And these are the highest and lowest points of the graph, respectively. Okay, let's look at another example. All right, so I want to find the absolute extrema of f of x on 0 to 1. So instead of writing that over and over again, for the next problems, I'm going to be doing the same thing, given the function and the interval on which we're going to find the absolute extrema on. Okay, so let me rewrite this a little bit. This will be, okay, our function is 3x cubed plus 3/2 x squared minus 2x. Okay, so first things first, we're going to find the derivative. So f prime of x is going to be 9x squared plus, when we bring the 2 down here, it will cancel with the denominator, so it'll just be 3x minus 2. Right, and we're going to set this equal to 0 and solve. Now, some of you may not see that this factors exactly. You can always use the quadratic formula, but this is a case where we'd use the AC method. So you can take the 9 and multiply it by 2, which gives you 18. And we want to find two factors of 18 that sum up to be 3, and specifically negative 18. Okay, so it looks like to me it would be 6 and negative 3, right? 6 times negative 3 is negative 18. 6 minus 3 is positive 3. Now you might wonder why we would do this, but it turns out that we split up the middle term with these two values. So it would be 9x squared plus 6x minus 3x minus 2. And the reason we do that is now we can factor both sides with grouping, or both groups with grouping. So we basically set up two things where they both, in their individual groups, share something. So here they both share, it looks like a 3x. So we can factor out a 3x and be left with 3x plus 2. And here they both share a negative 1. So we can factor out a negative 1 to get 3x plus 2. And now we have two terms that both share 3x plus 2. So we can factor that out. It's 3x plus 2 times 3x minus 1 equals 0. All right, and then that tells us that x is either equal to, in this case, negative 2/3 or 1/3. Okay, now here's where we have to be careful. Right, these are the critical points. However, we are restricted to this domain 0 to 1. So only 1/3 is in 0 to 1. Right, this is the symbol to mean is in, if you haven't seen that before. All right, so from here, when we go to check all the values, we don't need to worry about this negative 2/3. All right, so when we plug everything in, we're just going to plug in f of 0, f of 1/3, and f of 1. All right, now plugging these in, we get f of 0 is 0, of course. F of 1/3 is negative 5/3, and f of 1 is 2.5. A reason I didn't put this as a decimal, because with the dividing it by 3, we get like the non-terminating decimal, right? This is the negative 1.6 repeating if you want to do it as a decimal, which I guess is all right if you write it like that. So the absolute min is here, right? That'll be the 0.1/3 comma negative 5/3. And the absolute max is, of course, here, which occurs at the 0.1 comma 2.5. All right, so there we go. That is really all there is to it when it comes to determining whether certain critical points are absolute maxes or mins. You just compare them to each other and the endpoints. Okay, so for the next few examples, I just want to look at finding critical points of things that are a little more complicated. Okay, so I want to focus more on that part, because I think the plugging in and determining probably isn't what, hopefully, is giving everyone trouble. It's probably more how you find the critical points themselves. All right, so let's find the critical points of this function here. Say it's the function x to the 2/3 power times 2 minus x. All right, so to find the critical points, we need to first find the derivative and then set it equal to 0 and solve. So there are two ways we could go about doing this. We could either do a product rule, or we could distribute that x to the 2/3 and just use power rules. At the end of the day, I don't know if it's really going to matter. The thing to note is when you distribute this across, you of course get x to the 2/3 times 2, and then here x times x to the 2/3, well, this is x to the 1, which is x to the 3/3. So when it's all said and done, it's going to be x to the 2/3 minus x to the 5/3 when you add those exponents together. All right, so here we can just use the power rule. So f prime of x will be 2 times 2/3 times x to the 2/3 minus 1, so that'll be negative 1/3. That'll be minus 5/3 x to the, well, 5/3 minus 1 will bring us back to 2/3. Okay? And this is what we need to set equal to 0 and solve. So this is where I think a lot of people start running into problems. Okay? So there are a lot of ways we can go about doing this. Okay? One is if we were to simplify this to be 4/3 x to the negative 1/3, well, that negative exponent we can actually bring down into the denominator, right, to get 4/3 x to the 1/3 minus 5/3 x to the 2/3 equals 0. Okay, now to start with, right off the bat, we can't plug 0 in to this function, right? Plugging in 0 would cause division by 0. So this is a big thing to notice, that right, that f prime of 0 is undefined. Right, whenever you get x's in the denominator like this, that means you get an undefined value. Now here, 0, or actually nothing's going to mess this up because we're not dividing by it, right? But f prime of 0 is undefined, so that means x equals 0 is a critical point, right? It's not the kind of critical point we're maybe all that used to seeing, but it is still a critical point, okay? So this is one that you might miss if you're not careful, okay? So this is one of our undefined critical points. Now we're going to try and see where this is equal to 0. So my advice, whenever you have variables in the denominator, or really any denominator that you don't like in an equation, multiply everything by it. So I'm going to multiply everything by 3x to the 1/3. Okay? So we do that because when we have 4/3x to the 1/3 and we multiply it by 3x to the 1/3, well, we cancel out the denominator. Right? Then we'll have 5/3 x to the 2/3, and when we multiply that by 3x to the 1/3, well, the 3's cancel here, and then x to the 2/3 times x to the 1/3, those are going to play together nicely because when we add the exponents, we'll get x to the 2/3 plus 1/3, which will be x to the 3/3, which will become x to the 1. Perfect. Okay? Which will be 0 times x to the, or 3x to the 1/3, but that's still just going to be 0. So it's not going to change the 0 side. Okay? Now we're going to get 4 minus 5x is equal to 0, which makes our equation so much nicer. We just move that 5x over and divide to get x is 4/5. Okay, so the critical points are 4/5 and 0. Right? So 0 is the one you might miss if you're not really careful about the fact that the function, or the derivative of the function, is undefined at 0. Even though the original function is defined at 0. There's nothing here, like this function is nice and continuous everywhere. Okay? However, if we take a quick look at the graph, okay, here's the graph of this function, and we can see at 0 we have a spike. Right? It's a local min, but specifically it's a spike. And so we found that that was a critical point where the function was undefined. Okay? Similarly, we also see a turning point around in here, which should be at 4/5. Okay, and that's a nice thing here is that just looking at the graph, I can't really tell where that turning point is, but thankfully I already analytically know it's where x is equal to 4/5. Okay, so be on the lookout for things that will cause a derivative to be undefined. All right, so let's find the critical points of f of x equals x squared times ln x. Well, right off the bat, x squared ln x, the domain of this function is basically x is greater than 0, right? We can't put negative values into natural log. We can't put 0 into natural log. So we're basically only looking at values from 0 to infinity as our domain. Okay, so if we find any critical points outside of these values, or say we find one that's 0, we know that that's not really a critical point. Okay, so let's start with the derivative, right? F prime of x. Well, we're going to use the product rule, right? So x squared ln x, we're going to have 2x ln x, so derivative of the first, second guy left alone, and plus the second guy, or the first guy left alone, and the derivative of the second, which will be 1 over x. All right, so this will be 2x ln x plus x. Now, one thing to note here, we can actually say factor out an x, right, to get x times 2 ln x plus 1 if we want. One thing to note here is we can't plug 0 into this. However, that does not make 0 a critical point, right? So note, f prime of 0 is undefined, again. However, 0 is not a critical point because it's not in the interior of the domain. It's not even in the domain, right? So x of 0 is not a critical point because 0 is not in 0 to infinity. And we could say the same thing about -1, -2, etc. The domain of this function is also 0 to infinity. That's still the domain of the derivative. Okay, nothing's really changed. All right, so really all we need to check on is what makes this function equal to 0. So set x times 2 ln x plus 1 equal to 0. And note, you'll get x equals 0 as one of the solutions from this piece. All right, however, that's not in 0 to infinity, so we can actually throw this value away. We don't need to worry about it. We only really need to worry about the 2 ln x plus 1 equals 0. Okay, well, not too bad. We'll just move the 1 over and divide. So 2 ln x is equal to -1. Divide by 2 to get natural log of x is equal to -1/2. And if natural log of x is equal to -1/2, that tells us that, well, if we just incorporated e into this, we get that x is equal to e to the -1/2. All right, which is also known as 1 over the square root of e. All right, so this is the one critical point that we have. All right, and if we graph this, we see that there's some sort of a local minimum around 0.6, and when you calculate or approximate with your calculator 1 over square root e, right, you get about 0.6065. So that does jive with what we just found. So the turning points around here, and you'll notice that the graph doesn't exist past 0. Okay? Because ln doesn't. All right, what if instead we start with something with an e to begin with, like x cubed times e to the -x? Well, again, we take the derivative, which in this case is going to be a product rule. So 3x squared e to the -x plus x cubed times negative e to the negative x. If we simplify this a little bit, we'll get 3x squared e to the negative x, then minus x cubed e to the negative x. Now, one thing to note, e to the x and x cubed are continuous everywhere, and this will be too. So nothing is going to cause this to be undefined, right? So this will be defined everywhere, so we don't have to worry about that. So now we just set this equal to 0 and solve. Now, when you set anything with e to the stuff equal to 0, one thing to note is that e to anything, right, any real number, I should say, is going to be positive, specifically non-zero, okay? So that means we can actually safely divide out this e to the negative x. E to the anything, really, because e to the anything is positive, so we can divide it safely, right? And so this is usually why we don't divide by things with variables in them, is because they might be equal to 0, and we might be missing some important information. But e to the stuff will always be nice and positive, never equals 0, so we'll never be dividing by 0. So we get down to this equation instead. 3x squared minus x cubed is equal to 0. And now we can just factor out the x squared to get x squared times 3 minus x is equal to 0. So using the zero product principle, x squared is either equal to 0 or 3 minus x is equal to 0. So x is either equal to 0 or 3. So these are the critical points. Okay? So keep in mind with this e to the stuff, it may start off looking kind of gross, but just remember that it's really not as bad as it seems. All right, so let's find the critical points of this function. Let's say x times the square root of 4 minus x squared. And I do have a domain here because the domain of this function is negative 2 to 2. We basically need this to be positive. So we need 4 minus x squared to be greater than or equal to 0. So in other words, we need 4 greater than or equal to x squared, and that happens when x is between negative 2 and 2. All right. So when we differentiate this, once again, product rule, okay, we could move it to just be a chain rule, but I'm just going to leave it as a product rule for right now. Derivative of the first, which is 1, let me write that, 1, times the second left alone, right, plus the first left alone times the derivative of the second. So remember, square root of stuff, it's the derivative of the stuff over 2 times itself. So we'll just fill that in. And then the derivative of the stuff will be negative 2x. All right, so thankfully the 2's cancel there. And that x will multiply with that x. Okay, so we have the square root of 4 minus x squared, and then we'll get minus x squared over the square root of 4 minus x squared. Now, one thing to keep in mind is that negative 2 and 2 are not allowed here. Okay, however, those are not in the interior. They're the endpoints. So one thing to keep in mind is that here x equals plus or minus 2 will make f prime undefined. But they are not critical points, right? Even though they make the function f prime undefined, they're not critical points because they're endpoints, which means they're not in the interior. So if you're curious what I mean by the interior, if the domain is negative 2 to 2 closed, the interior is negative 2 to 2 open. Okay, so we can't include the endpoints of this as critical points. All right, so we don't really need to worry about that. So really all we need to worry about is when this is equal to 0. So here is how you go about solving things with square roots and fractions and whatnot. Okay, start by moving this piece over. Okay, so we're going to start by moving that over to get the square root of 4 minus x squared is equal to x squared over the square root of 4 minus x squared. Now multiply both sides by the square root of 4 minus x squared. When you do that, all right, you get 4 minus x squared times the square root of 4 minus x squared. Well, what is that going to do? It's going to get rid of the square root. Okay. Then we'll have x squared over 4 minus x squared times the square root of 4 minus x squared. Well, that's going to cancel this out. All right, so we're going to end up with, on this side, just 4 minus x squared, okay, equal to x squared. We've simplified that a lot now, so now we can move the x squared over to get 4 is equal to 2x squared. Divide by 2 on both sides to get 2 is equal to x squared. So then x is equal to plus or minus the square root of 2. Okay, and those are the critical points, and they are in the domain negative 2 to 2. Okay, square root 2 is like, I want to say it's like 1.4-ish. Okay. All right, so if we take a quick look at the graph here, we kind of get the information we're looking for. At about 1.4-ish and negative 1.4-ish, we have critical points, we have turning points, and then we see that the graph doesn't exist beyond negative 2 and 2, and there we are. All right, I do want to do one more example here to show you how you can tackle trig type equations here. So I do want to put it on an interval, because if we don't, we will have like an infinite number of solutions when we say take the derivative and set equal to 0. So I want to kind of restrict that to this domain here, negative pi over 4 to pi over 3. All right, to find the critical points, of course, you take the derivative, so f prime of x, that will be 3 cosine of 3x, right? Derivative sine of stuff is cosine of stuff times the derivative of stuff, which will just be 3. And now we're just setting that equal to 0. Okay, so we can basically ignore the 3 and just look at cosine of 3x equal to 0. Now, whenever you are thinking about solving a cosine of 3x equals 0, right, something like this, what you need to do first, don't worry about that 3x. First think, okay, if cosine of theta equals 0, what angles will cause theta, or what angles theta will cause cosine to be 0? Well, cosine is 0 for multiples of pi over 2, right? So plus or minus pi over 2, plus or minus 3 pi over 2, plus or minus 5 pi over 2. All right, I'm doing a few of them here. Okay, let's say plus or minus, nothing even up here, because 4 pi over 2 will just be plus or minus 2 pi, and that doesn't cause cosine to be 0. But like 7 pi over 2, 9 pi over 2, etc. Okay? All right, now, we don't have just a theta, we have a 3x. So 3x is going to be equal to these things, plus or minus pi over 2, plus or minus 3 pi over 2, plus or minus 5 pi over 2, etc. All right, so what we're going to do to get down to just x is divide by 3. All right, so x is going to be plus or minus pi over 6, plus or minus pi over 2, plus or minus pi over, or that would be 5 pi over 6, plus or minus, let me do the next one, 7 pi over 6, and then finally plus or minus, when we get to the 9 pi over 2, that will be plus or minus 3 pi over 2, because the 3's will cancel. And we could continue going. Now, the reason I did a bunch of these is because we have an interval negative pi over 4 to pi over 3. So I only want to pick things that are in this interval. Okay, so plus or minus pi over 6 should be in this interval. All right, so plus or minus pi over 6 should be there, because if you remember your number line here, here's say negative pi over 4, here's pi over 3. Sorry, I don't know what happened to my writing thing there. Here's pi over 3. Okay, pi over 6 is here. Negative pi over 6 is here. Okay. Plus or minus pi over 2, not in there, because that would be here and here. So, nope. Plus or minus 5 pi over 6. No. No. 5 pi over 6 will be here. Negative 5 pi over 6 will be here, so that's not going to work. Negative 7 pi over 6, again, not going to fit. So it looks like it's just going to be plus or minus pi over 6 that works. Okay, and so when we look at the graph here, we see that in that interval we only do have two turning points, negative pi over 6 and positive pi over 6. Whoops. Okay, so those would be the only two there. All right, so that is one way you handle trig functions. Now, the reason I did so many is because a lot of times, even though these did not end up being in the interval, a lot of times they will be, right? If we had a bigger interval, we definitely could have seen a lot more of these pop up, right? If we were doing negative 2 pi to 2 pi, we'd see a lot of these, right? So, anyway. All right, I think that should be enough to get you rolling on the homework, and I will catch you on the next video. Cheers!